Hello, everybody. Today we will be learning chromatography. So chromatography, their purpose is to separate mixtures. And in the chemistry syllabus, most of the time you will be separating a mixture of amino acids. So there are two types of chromatography. That means there are two types of separation. So number one, we call the adsorption separation, the first type. Okay, so the mixtures are separated based on adsorption. The second type is the partition separation. So it's just two different ways of separating your compounds apart. So the first one is adsorption. And how do we define adsorption? Adsorption separation is based on different interaction. Interaction is affinity attraction between the compounds, your sample, so-called your amino acid, with the stationary phase relative to their solubility with the mobile phase. So every chromatography will have a stationary phase and a mobile phase. So when the compounds are separated, it's either A, they choose to interact with the stationary phase more, or they choose to be more soluble with the mobile phase. Okay, so that is called an adsorption separation. So please take note on the terms you use. Please don't write interact with the stationary and interact with the mobile phase. That is not correct. Stationary phase is the word interaction, affinity, or attraction. Mobile phase, you use the word solubility. The example that we're going to learn here is called the thin layer chromatography, TLC in short. Okay, now the other type of partition is based on, let's look at the definition. So it is based on different solubilities between the stationary and the mobile phase. This is more straightforward. It means that you choose to be more soluble with the stationary phase, or you choose to be more soluble with the mobile phase. Now, solubility means the compound can have appropriate interaction with the solvent that is moving. Mobile phase means a phase that moves, and it will be your solvent. It can be any solvent, okay, like water. It can be an ester. It can be a mixture of a water 30% and ester 70%, or it can be a mixture of 3 or 4 solvent together. So that will be your mobile phase. Is definitely a solvent with different percentage of composition, and it moves. That's called the mobile phase. So anything got to do with mobile phase is solubility in the mobile phase. It's only the difference where the stationary phase comes in. If you're the adsorption type, you choose to adhere at the surface of the stationary phase. So stationary means is a solid that does not move. All right. So it can be like a paper. All right. As simple as a paper, it can be a plate. Okay. So then the paper or your plate here will be your stationary phase, and the molecules can choose to interact with the stationary phase here. They can choose to have an appropriate interaction with the paper or with the plate. All right. So you may want to use your understanding on intermolecular forces here. So the one that can form, for example, non-polar and non-polar. So if your compound is non-polar, then they will interact very well with a non-polar type of stationary paper or a glass or a plastic. All right. Yeah. So based on appropriate interaction, so non-polar compounds will bind more appropriately with the non-mobile stationary phase. All right. And of course, your stationary phase can also be polar. All right. So if your stationary phase is the polar type, then samples or compounds that are more polar are able to interact well. The word is interact well with the stationary phase. Okay. So when we flush the sample through, when you have a mixture, you have mixture of polar, you have mixture of non-polar. So it depends whether your stationary and your mobile phase, which one of them are more non-polar or which one of them is more polar. So the polar will be more siding to the polar phase, be it stationary, be it mobile. The non-polar will be siding to the non-polar phase, be it your stationary or your mobile phase. That is a general concept, okay? But what I want to highlight the difference here between adsorption and partition is that the words that you use between the stationary phase for the two type of separation must be very clear, all right? Interaction is interact at the surface of the stationary phase. But then let's look at partition. Why partition for stationary phase? We use the word solubility. It's because for partition type of chromatography, they actually have a solid phase, all right, which is a so-called wire to you. Maybe it looks like a wire, a metal wire, but we call it a column. All right. Okay, so you can just treat this like a solid, a wire, or a plastic. It doesn't really matter what is it now. So it's just a solid. Okay. What they do is they coat a liquid. So they coat, it's like you spray hair gel. All right. So you spray a liquid that is fixed onto a solid surface. All right. Now that liquid here is the one that is fixed or stationary on your glass, your wire, or your plastic. And therefore, your compound can choose to be soluble into the fixed liquid stationary phase. So when they soluble, also called interact appropriately, the interaction, we call this as solubility. But of course, we also need to bring in our intermolecular forces. Okay, yeah. The difference basically is the word interaction and solubility. So that is the first part that I want to cover, which is the definition of adsorption and partition. Now, the example of the partition separation would be our GLC, so-called gas liquid chromatography. Now, gas liquid chromatography, it means that it can separate gas, it can separate liquid. So maybe, for example, you have a liquid sample that inside has many types of amino acids, and you want to separate all the maybe 20 amino acids that's currently now in liquid form. So you can inject the liquid into the machine and they will boil it up into gaseous state. Okay, so eventually you can inject gas sample, a mixture of gas you can inject a mixture of liquid, and then the machine will have an oven to boil up, okay, or evaporate up the liquid sample. Now, if you were to inject gas sample already, then the oven is there to maintain the compounds in gas, to prevent them from cooling down to room temperature, and basically it's trying to maintaining them at gaseous state. All right, because eventually the one that's moving will be gas molecule. All right, so if you inject liquid, it will be evaporated up or boiled up to gas. If you inject gas, then it's already gas. It will still be in the oven to ensure everybody will be in gaseous state. Okay. Now, so I have covered the difference. Now, the next section is I'll go in very detail for the adsorption separation first, all right, which is the thin layer chromatography type. And then perhaps the next section or the next video, I will cover the GLC. So for the thin layer chromatography, okay, first thing I need you to know is I want you to know what is the composition of the mobile phase and the stationary phase. So you can see this is a very simple picture to show what is called a thin layer chromatography. You have a beaker here, as you can see, and you have solvent. This solvent is called your mobile phase because liquid solvent can move. They will be moving upwards, all right, on your stationary phase, all right, via capillary action. Okay, now, then this so-called vertical solid here, now it can be a plastic, as you can look at my cursor. It can be a glass. It can be, most of the time, aluminum foil. Yes, it can be plastic. It can be glass. It can be aluminum foil. Okay, and then you coat it with a thin layer of aluminum oxide. Another one would be silicon dioxide. Okay, so you can spray a very thin layer of alumina, Al2O3, or silica, SiO2, onto a glass, onto a plastic surface, or onto an aluminum foil. Okay, so that alumina or that silica that is supported on a glass or plastic or an aluminum foil will be your stationary phase that's not moving. So you put it in your beaker. all right? And then the mobile phase will move upwards via capillary action. Okay, so first, please memorize what is the stationary phase and what is the mobile phase. Now, your mobile phase can be any solvent. All right, you can just write any solvent. You want to write, you can write polar, you can write non-polar. But I suggest you just don't be too specific. You can just write any solvent will do. Okay, yeah. Now, that's the second part that I need you to know. Okay, first part is adsorption partition. All right, second part here is what is stationary phase and mobile phase for the thin layer chromatography. Okay, part 3. I want you all to know what is the baseline. Okay, part 3 here. So I'm going to highlight, let me change the color. I want you to know what is called a baseline. Okay. Okay, I will just write over here. So this line here is called the baseline. All right, baseline. And let's say there's another line here. This is called the solvent front. All right, so please imagine the stationary phase, right? When you have to drop your mixture of solute. All right, please draw a line, take a ruler, draw a line here. This line is called baseline, which is the starting point. And you drop a mixture of your maybe amino acids over here. Okay, now then you put it into the beaker, which already has your mobile phase. And please cover with a lid because you need to saturate the beaker with the mobile phase, okay, the atmosphere, okay, you have to close it. Now then, as time goes by, the mobile phase, so-called solvent, will move upwards the alumina or silica that is supported on a glass or plastic sheet. Okay, so it becomes wet. And as you can see, when it moves upwards, right, there is a gray line there to indicate the so-called wet region. Okay, now you can stop the experiment at any point of time, but you have to stop it before the whole alumina or your whole stationary phase become fully wet. So let's say you stop until here. So this is the gray line, okay, that indicates that this whole part was already so-called wet or so-called moved by the stationary mobile phase, okay? And this top part here is still dry. Okay, this top part is dry. So you can see a gray line to separate them from the wet and the dry region. So you have to stop the experiment anywhere, any point of time you like, so long the whole alumina is not fully wet. Okay, now once you choose when you want to stop the experiment, quickly take out the glass plastic, out and quickly draw a line. So this line here, you take a pencil and ruler and draw. This is called the solvent front. This is until where your mobile phase has moved. We need to measure the distance of the solvent front, how far, how long your mobile phase has moved. All right. And of course, when the mobile phase moves, it will start to separate your mixture of samples, maybe amino acid apart. So as you can see here, there are 1 sample, 2, 3, and 4 amino acid. Initially, the mixture contains 4. After chromatography, I realized inside there are 4 types of amino acid. Okay, now, so baseline and solvent front, you have to know because we need to measure the line. Okay, now that is the term that you have to know where is baseline and where is solvent front. The next important thing that I want to bring up is the word called the thin capillary tube down here. Okay, now, so there was a paper 5 question that asked, how do we put place our mixture of samples on the baseline, okay, which is here. So you can look at my cursor here. They ask, how do you put? They actually ask something about a thin capillary tube. Okay, now, the correct answer is you have to use a thin capillary tube. All right. Can you see this picture here? This is basically like a very, very fine thin glass. We call this a thin capillary tube. Okay. It is made from glass, a tube, which is bigger, and they need you to pass through fire. So for example, just imagine that this is a fire here, and this is the glass. All right. I need you to hit the glass. okay, hit the glass. It's a tube, you hit it, and the glass would melt because it's very, very thin. So when it melts, right, I need you to pull the glass apart, and it becomes very fine, very fine, very fine. At one point of time, all right, it's going to be too thin, right? Immediately after that, you take off from the fire, and I need you to snap it apart. So when you snap it apart, right, that thin part that you pull is going to be very thin. Okay, yeah. So we will use that part there, the thinnest part there, to transfer our sample from your maybe test tube or maybe your microcentrifuge tube and place it on the baseline. So you can see here, the picture shows that this person is actually placing the sample using a thin capillary tube, okay, on the baseline of the stationary phase. Now, please do not go and suggest use a pipette, okay, because at your level, the only pipette you probably would use at A level would be the 25 centimeter cube volumetric pipette. And please do not use dropper like what you use to extract out for qualitative analysis. You use NaOH, NH3 to test for cation types. Don't use that, all right? So you cannot use pipette or dropper, okay? So the question asked in paper 5 was, why do we need to use a thin capillary tube to place the sample on our baseline, and why we cannot just use, like a pipette or a smaller pipette or a dropper? Okay, the answer is because thin capillary tube enables the application to be more controlled. Okay, so that would be the answer from the marking scheme. Maybe some of you will start thinking that, if I use a thin capillary tube, the application sample volume can be very, very small. I don't need to use like a very big dropper that utilizes a lot of sample on it. Yes, it sounds right, but you still can place a lot of volume using a thin capillary tube. It's just that you need to do it multiple times, right? Because we want to ensure a lot of the mixture was on your baseline. All right, so you can see a more clear and darker intensity of separation. You also can do, but it's just that you have to do it multiple rounds for the same volume. If you use a dropper, one drop, maybe it's already maybe like 1-2 ml. But for the same 1-2 ml, you need maybe like 50 to 100 times of, thin capillary tube to transfer. So the difference between these two is, one is more controlled. You can control it to a very tiny small spot. And the other one is one lump sum, you transfer 1 centimeter cube. So you're going to have a fat drop there. Okay, yeah. So that is what is called a thin capillary tube, and the function and why we use a thin capillary tube. All right. So before I move to the next section, which is an example, I would like to sum up what you need to know on this particular screen that you're looking at now. Thin layer chromatography, number one, you need to tell what is the stationary phase, what is the mobile phase. Number two, you need to know what is solvent front, you need to know what is baseline, and you need to know what is used, which is a thin capillary tube to transfer your sample onto the baseline. All right. Now, we shall proceed with one particular past year here, which is a summer 1942, question 7. Okay, I'm going to continue using this past year to teach you how do we quantify, all right, and identify after you run your thin layer chromatography experiment. So over here, you can see this is your baseline. This is your solvent front. And your examiner has given you a so-called ruler printed on your question paper, and they gave you some RF value. So let's learn what is RF value. RF value is called as the retardation factor. It is defined as the distance traveled by the solute, which is your compound, divided by the distance traveled by the solvent. Now, do you understand why we need to have a baseline and solvent front? Because the distance traveled by the solvent, okay, is this distance, which is 5 centimeter. So the question later on, the distance traveled by the solvent is 5 cm. Okay, now then, the distance traveled by your solute. So for example, you had a mixture of amino acid and you don't know how many you have. But after running this experiment, you realize there's 2 dots coming out, which is dot A and dot B. So dot B, you take a ruler and you measure the distance here is 1.5 centimeter. And for the spot A, this would be 3.5 centimeter. Okay, so the retardation factor, all right, will be the distance traveled by your A divided by the solvent front. So let's solve the first question over here. Okay, so this is the quantification part. You need to quantify what is the retardation factor. which is from your thin layer chromatography. Okay, that would be quantification part. Now, use the chromatogram and the RF values to deduce the amino acid responsible. So if you want to identify what is the amino acid identity, right, you need to first quantify, then the numbers, you match it with a spectral of library. So in this case, the examiner is giving you a table of, okay, if you're 0.4, you are alanine. Congratulations, you know who is the sample. Okay, now, so let's quickly calculate what is the amino acid responsible for A. So we need to calculate the retardation factor for spot A. So spot A is the distance traveled by spot A, which is 3.5 centimeter, divided by the distance traveled by the solvent. So centimeter and centimeter, you cancel off. Therefore, spot A has a 0.7 retardation factor with no units. So 0.7, you look at the table, you know that spot A is leucine. All right, and you want to know what is the identity of the spot B. So you calculate the retardation factor for spot B, the distance traveled by spot B, which is 1.5 centimeter, divided by 5 centimeter. So therefore, the number will be 0.3. So 0.3 here, you look at the table, the closest will be glutamic acid. So that will be the quantification and identification part. Okay, now part 2. A second chromatogram of the same mixture is taken using a more polar solvent. Predict the effect of the RF values of the amino acid and explain your reason. Okay, now, first, we need to understand why did spot A move further or longer distance, which is 3.5 centimeter, and why did spot B move a shorter distance. Okay, now, over here, let's look at the notes. Compounds that travel slower upward, in this case, it will be spot B. All right, he only traveled 3.5. Sorry, 1.5. Okay, 1.5. He only traveled 1.5 from the baseline. Okay, now it means that the spot B or the amino acid B interacted very well via appropriate intermolecular forces with the stationary phase. Okay, so that means he kind of like hugged the alumina and the stationary, which is the one that is not moving, and he doesn't want to move. But eventually, he still managed to move upward with a very, very short distance, very reluctantly, because he bind or interacted well with the stationary phase. Okay, maybe hydrogen bonding, maybe permanent dipole interaction, or maybe just a instantaneous dipole-induced dipole interaction. So if you travel very short, it means that you interact very well with the stationary phase. Now, for compound A traveled faster and longer outwards. So for A, he traveled 3.5 centimeter. Okay, now why did A travel so fast for the same amount of time for the same experiment? Okay, now it means that amino acid A was more soluble with the mobile phase because the mobile phase or your solvent will move upward via capillary action. All right, now, so when the solvent touches your mixture of amino acid, they would bind via interact molecular forces with the amino acid A, and then amino acid A and your solvent will have appropriate intermolecular forces, okay? And therefore, mobile phase will carry the sample upward very fast, okay? It will carry the sample up. So if you so-called favor the mobile phase, you would move with the mobile phase upward very fast, okay? So we talk about solubility with the mobile phase. Okay, now, then we come back to here. All right, we come back to here. A second chromatogram, right, was used, but using a more polar solvent. Okay, now, predict the effect on RF values on the amino acid. Now, first and foremost, you need to have a little bit background on amino acid. Okay, now amino acid, you have an amino group here. You have a central carbon, and you have a carboxylic acid, and this is your R. Now, there are 20 types of R here, which accounts for the 20 types of amino acid, okay? But the basic structure is a amino a CH and a COOH. Now, first and foremost, the amino acid backbone, it would be polar, all right? Because when you open up the structure, right, your nitrogen here is trigonal, pyramidal, okay? And then on the right-hand side, you have a trigonal planar, COOH. The backbone itself is already polar, okay? So when you use a more polar solvent to carry up, okay, the same mixture, okay, how would the amino acid A and B, in terms of the RF value, would change? Okay, yeah. Now, so first, amino acids, they are actually polar. And if you use a more polar solvent, amino acid being polar, and a more polar solvent, they are able to interact well. Okay, they are able to be soluble, more soluble, because polar compound, which is amino acid, and a more polar solvent would interact appropriately. Okay, if you use a same polar amino acid, but the solvent is non-polar, so a polar and a non-polar will not be able to interact well. Hence, they won't move that far. But if your amino acid is already polar and your solvent is even more polar, so polar and polar, the mobile phase will interact very well via solubility here, and it will carry up the amino acid very fast. And we're talking about both A and B spot, because A and B both are amino acids. All right. So the answer over here is we need to first address to say that since, all right, amino acids are polar molecules, okay, therefore, they will be, your amino acid is there, they will be more soluble. Remember, use the word soluble with mobile phase. Cannot say interact, all right? They'll be more soluble, okay, in the mobile phase. You can write mobile phase, you can write your solvent, okay? Yeah. That's it. Like this. Okay, that would be the answer. Now, so the last part on what I have covered with you, which is explain high RF values and low RF values. Okay, high RF, also called high retardation factor, it means that your numerator is big. Okay, high RF value, it means that you are more soluble with the mobile phase, which is here. If you want, you look back here. High RF value, these will contribute to high RF values because you are more soluble with the mobile phase. Okay. Low RF value means the numerator was smaller compared to the denominator. So therefore, it means that you unlikely move, you don't really move that far upward on the stationary phase is because you prefer the stationary phase. Okay, so you interacted very well with the stationary phase. So that would be on everything on thin layer chromatography. Okay, so before I sum up and close the section on the thin layer chromatography, okay, number one, with regards to thin layer chromatography, you need to know that thin layer chromatography is an example of adsorption, separation. Okay. And you need to know what's the definition of adsorption separation. Okay. Now then part A, are you able to list down for me what is the mobile phase, which is a alumina or silica sprayed onto a glass or a plastic, or it can be aluminum foil. Stationary phase, okay, it can be any solvent. Part B, do you know where is the baseline? Do you know what is the solvent front? Where is the solvent front? Do you know what is being used and why, which is thin capillary tube is being used to transfer your sample onto your baseline? Number three, how do we quantify and identify? your mixture. So the quantification here, we use retardation factor. Which is known as RF values. So the distance moved by your spot over the distance moved by your solvent. Okay, and how do we identify? You need to match with a library, a reference table given. Okay, so you can identify. Now, part 4, high RF value means, okay, high RF value means you are the compounds, okay, are more soluble in the mobile phase. Then you may want to write what is the intermolecular forces. But for that particular question, I can't write. It's because they just say polar. So maybe if you want to say PD or hydrogen bonding, it's still quite vague because polar, we don't know what is the solvent they use, which is so-called claimed to be more polar. All right, so we can't really comment on what type of interaction. Low retardation factor means compounds interacted more with stationary phase. All right, so that will sum up what is the thin layer chromatography section. Okay, now subsequently, we shall move to what is the gas liquid chromatography. Okay, so I'll continue with part 2 here. So gas liquid chromatography, it's another type of example, but the separation is based on solubility between the stationary and the mobile phase. All right, it's either you choose to be soluble with the stationary phase, which is a liquid coated on the solid, or you choose to be more soluble with the mobile phase that carry you through. Now, everything in GLC eventually is in gaseous state. Okay, yep. Now, first thing, okay, mobile phase and stationary phase have to know also. Okay, so let's look at this picture here. So same thing with the same backbone. All right, part A, I need you to tell me what is the stationary and the mobile phase. So the stationary phase here is an inert gas. All right, so they will carry and so-called flush or blow through. They'll try to push all your samples, the mixture, to separate them. Okay, yeah. So since everything is in gaseous state, be it you inject a liquid, so can you see there's an injection point? So this injection point here, you can inject a sample, a mixture of gas, or you can inject a mixture of liquid sample in, okay? And can you see there's an oven here? So the oven will evaporate if you are liquid, okay? And to ensure whatever that is in gaseous state will remain as gaseous state, okay? Because your mobile phase here is a inert gas that will not react with your sample. So you can just write mobile phase is any inert gas. And if you want to give an example, you can give helium, you can give argon. All right, they are the noble gases. So just select inert, okay, to prevent from reacting with your sample. So your mobile phase is inert gas. Okay, now your stationary phase is who? So please look at this column here, the word column. It actually looks like a wire, okay, but it's a very thin, fine wire that we do not call it as wire, we call it as a column, right? Now, column, it's a coil and it's very long. Obviously, a longer column, all right, so-called a longer marathon, will able to separate your compounds better. All right, so that's the reason why it is so long and they had to call it. Okay, yeah. So it's just like running a marathon. The longer the marathon, the better you can separate your runners. The shorter the marathon, the less you are able to separate the runners properly. Okay, yeah. So I want you to look in the close-up section of the stationary phase called the column. Now, as you can see down here at the bottom picture here, can you see here I label stationary phase? Now, this stationary phase is your column. All right, now please don't write column as stationary phase. Your stationary phase, please write, it is a high boiling point. High boiling point means take a very high temperature to make you in gaseous state, very high, because you are actually all in an oven now. you need to ensure that after putting the column in an oven, the stationary phase do not evaporate out. Because if you also become gas, your sample is gas, your stationary also boiled become gas. So everybody is gas, then there is no stationary phase, and you're going to get a lot of complicated signals coming out at the detector. Okay, so you want to ensure that your stationary phase don't move, don't boil, become gas. You should be a high boiling point, also known as non-volatile and non-polar liquid. All right. Most of the time, we will be using non-polar liquid and maybe hydrocarbon most of the time. Okay. So you need to coat the inner layer, as you can see here. The inner layer of the column, all right, is coated. All right, the inner layer, they coated with a very high boiling point or a non-volatile a liquid, and normally the liquid is a non-polar type. Okay, so when the gas travel, right, okay, the compounds may be stuck to the inner wall of the column. All right, but of course, when they are stuck, your mobile phase, which is the inert gas, will constantly push them to make them finish the marathon. It's only whether you finish the race or you finish the marathon with a longer time or a shorter time. Correct, not? So the first part about the gas liquid chromatography is you need to be able to list down what is your mobile phase, what is your stationary phase. That's number one. Okay, now number two, I want to talk about part two. How is your sample being separated? So the samples are being separated based on two things. All right. Number one, volatility. Number two, polarity. Okay. Now, because everybody is in gas state now. Okay, gas. So let me highlight volatility, and the second is polarity. So more volatile compounds will travel the column faster. When you have a mixture of compounds, some has a low boiling point. They boil up faster and become gas faster. If you become gas faster, then the mobile helium argon gas will push you through and you travel the column first. Then obviously you have an upper hand. You may finish the whole column and reach the detector at a shorter time. Okay, so that is if you're more volatile, you will travel the whole column faster, and therefore, when you are being detected, is a shorter retention time. Okay, so retention time, define, very good. So let's look at what is called retention time. So called the time taken for you to finish the marathon. So retention time, please look on top, red color font. Retention time, you can define it as the time for the compound to stay in the column, or the time for a compound to travel through the column, or the time between injection and detection on the computer screen. Okay, so the time taken for the compound to travel through the column, of the time for the compound to stay in the column. All right, yeah. So the mobile phase is constantly flushing and encouraging the mixture of amino acid or compounds to move through. All right, so volatility, that's the first one. Okay, now the second factor is polarity. So because most of the time, our stationary phase is a non-polar, high volatile liquid that is coated at the inner wall, all right? The more non-polar the compound, okay, the more soluble it will be with the non-polar stationary phase. So I will make an assumption because most of the time, our stationary phase is non-polar. So if you are the sample and I am the inner wall, which is the stationary phase, and I happen to be also non-polar. So you're the sample non-polar, I'm the stationary phase non-polar. Non-polar and non-polar are able to interact well via ID-ID interaction, which is instantaneous dipole-induced dipole forces. Okay, so non-polar and non-polar, they will mostly bind. Okay, and we do not say interact, we say more soluble. Remember? What is partition? Partition is defined as the separation based on different solubilities between the stationary and the mobile phase. You either choose to be more soluble with the stationary phase or more soluble with the mobile phase. So the word you need to use here is soluble. So if you're non-polar, you are more soluble with the non-polar stationary phase via ID-ID interaction. Are we clear? Okay, yeah. So if you are polar, then you'll be less soluble with the non-polar stationary phase. Okay, so therefore, a shorter retention time, that means you travel the column quite fast. A shorter retention time, okay, means you are less soluble, okay, with stationary phase. If you took a long or you reported a high retention time, that means the time taken between injection and detection is very long. It means that you were stuck in a column for a very long time. The reason why you're stuck is because you are more soluble with the stationary phase. Clear? Okay, so that is how you're going to answer in your exam. Okay, now, so the quantification is the software program. Okay, the detector on your computer, they will tell you the retention time, they'll give you a number. So that's the quantification part. Okay, and of course, how do we identify the unknown? So as you can see here, this is called a chromatogram here. Okay, this is a chromatogram. So it's going to be on your computer screen. And on the x-axis is called the retention time. On the y-axis is literally like the number, okay, or how high intensity is the signal, basically. So you have high signal means you have a lot of that particular sample. Maybe spot A, you have high sample, that means you have a lot of spot A in your mixture, okay? Yeah, so that is the chromatogram. So I already covered what is the identification method, which you don't need to calculate anything here. The computer will tell you the retention time. And then the identification method is just the software program will tell you, okay, 5.2, they'll tell you the identity is this amino acid, all right? Or 1.2 minute, they also tell you that it is this particular amino acid or this particular component, okay? Now, continuing, there is more quantification to be made, okay, which is a simple math. And I'm going to bring up winter 22, 42 past year up, all right, to so that you can gauge what is an example of calculation that comes out, okay? Now, so let's look at this particular past year here on GLC. Now, so gas liquid chromatography involve a stationary and immobile phase. Now, number one, name or describe in detail a suitable substance that could be used for each phase. Okay, so you know, all right, they will normally ask what is your stationary, what is your mobile phase. So for stationary phase, can you still recall? It is a non-volatile, okay, non-volatile, non-polar liquid that is coated at the inner wall. All right. Non-volatile, non-polar liquid. Okay, normally non-polar is not the mandatory word, but non-volatile is a mandatory word. It's because you need to ensure that they do not become gas as well, your stationary phase. Mobile phase, you can write inert gas. Or you can put a specific identity called helium or argon or nitrogen gas, also can. Okay, now, so let's look at this chromatogram here. So you can see you have the recorded response on the y-axis and the retention time on the x-axis. So a mixture of three organic compound is separated by GLC, and the chromatogram obtained is shown in figure 9.1. The amount of substance is proportional to the area under the peak, obviously. So when you have more area or higher surface area, it means you have more of that particular amino acid in the total injection sample you have put. Now, number one, explain the meaning of retention time. Do you still remember what is the definition of retention time? So what is retention time? Retention time is the time that the substance travel or stay in the column. okay? Or it can be time between injection and detection, accepted. All right, now, next, calculate the percentage of B in the mixture. Percentage of B means what is the amount of B in the total mixture. So obviously you need to calculate what is the area of the triangle B, all right, over the total triangle. Now, so everybody, how do you calculate triangle, class? Half times height times base. Well, you can pause the video at any time, all right, and do the calculation, all right, but I'll just continue, okay? I will suggest you try it first and pause the video, and then you only continue and see the discussion. So for B, half times height, half times base times the height. Okay, now, so what I can see here is B covers 3 over here. You look at the x-axis, it covers approximately 3 intervals. All right, if you were to take a ruler and if you calculate out per interval here or per line is actually 0.2 if you calculate out. Okay, one small box is 0.2 on x-axis. So the base is 3 times 0.2. That is on the x-axis. That's your base. Okay. Your height, if you take a ruler to the y-axis, is 100. So therefore, the area for B is 30. Okay. Yeah. Now, so you can see 20 to 22. Look at the cursor. 20 to 22 is 10 small boxes. That means one small box is 0.2. Okay, and the base of B is 3 small boxes. That's why it's 3 times 0.2. Okay, now then if we were to do for C, half times base. Now the base over here, very clear, 2 small box, which is this. The height, if you take a ruler, is 25. This would be 5, the area for C. And the area for A, half times base. If you look at the x-axis on A, it covers 2 small boxes. So 2 small boxes per box is 0.2. The height is 30 on the y-axis. Therefore, the area is 6. Correct? So what is the percentage of B in your mixture? So you will take your percentage of B is 30 divided by 6 plus 30 plus 5 times 100%. You will calculate to be 73.2%. All right, so you have 73.2% of B in your total mixture. All right, so this one is also the quantification part on the gas liquid chromatography. Okay, so far, so good, everybody. Okay, now I'm done with the gas liquid chromatography already. And before I close everything up, and I want to do a short summary. Okay, number 1. Okay, I put number 2. For gas liquid chromatography, first, they are an example of a partition. Type of separation. They are partition chromatography. All right, separation base. And are you able to give me definition of partition separation? ... You fill in the blank. Okay, now part A. Who is the mobile phase, or what is the mobile phase for your gas liquid chromatography? So you want to put that inert gas. For stationary phase, you put a non-volatile, non-polar, liquid. Okay, now then B. In GLC, the mixtures are separated by Maybe I should type. I think type would be faster for me. Come. Let me just do a quick type. Come. Okay, mixtures are separated via number 1. Okay, part B, volatility. Okay, so volatility is the more volatile the compound, the faster it travels, and the shorter the retention time. Okay, the more volatile the compound, the faster it travels, or the other way around. The less volatile the compound, the slower it travels, the longer the retention time. That will be volatility. Mixtures are also separated based on polarity. Okay, the more non-polar your compound, the more soluble it will be with the stationary phase. The other way around, the less, or maybe the more polar, the other way around, the more polar the compound, the less soluble it will be with the stationary phase. And this is with the assumption that your stationary phase is non-polar, because most of the time it will be non-polar unless your examiner choose to change your stationary phase to become polar. Okay? Like this. So that will be part B. Now, part C, okay? Part C here, retention time. So retention time, what is the definition? The time, okay, you can pick any one of the 3 given just now, the time between injection and detection. Okay, and for retention time, the quantification method, retention time, and identify, how to identify is you just look at what is the retention time and you know the identity. Okay, now for quantification method, okay, you may need to calculate the percentage area of a compound, like the past question, in a mixture. All right, that will be part C. That's all. Okay, so all in all, GLC, we have completed. So this will sum up the whole chapter on chromatography. All right.